Hi, I put together this video to demonstrate a few aspects of factor analysis, and I'll be working on exploratory factor analysis, and I'll demonstrate some of the settings that you can use. I've got a data set here with 13 items on a Likert type scale. The scores are ranging from 1 to 7, and you might notice that there are some scores of 9, and 9 is specifically used here as a missing value. So whenever you have the value of 9, it's because the participant did not provide an answer. It's not a giant database. It's reasonably sized at 117. And, when you have some missing data, those ones potentially aren't going to be used for specific analyses. In this particular data set, we were originally, this is about 15 years ago that the data were collected. We were originally just pilot testing some items to see how well they would work. And these items are in reference to attitudes about the sex offender registry. What do people think about the sex offender registry? If you toggle over to variable view, you can see the items. I have them loaded in here. If I found out that a sex offender was living in my neighborhood, I would consider moving. Public motivation to take action against sex offenders is a goal of the registry, and so on. So each item is a statement that the person can strongly agree with or disagree with. Let's take a look at the codings for the response options. You can see that it's 1 to 7 scale, strongly disagree, going up to strongly agree. There are no reverse coded items in this particular set of items. So my goal here is to just very basically provide a tutorial on how to set up a factor analysis using exploratory factor analysis, and I'll demonstrate some of the settings. So let's go to factor, analyze, and then dimension reduction factor. That's the pathway to get to factor analysis. And what I'm going to do is I'm going to take all 13 items and carry them over into the variable box. You can do that by pressing the shift key and then clicking on the first and last one. Let's go through all the different options. We need to change a whole bunch of different options that are available to us. In the default settings, SPSS does not really set it up well for factor analysis. And I guess the reason why is because there's so many different options in factor analysis that they don't want to presume specifically what you want to see. But there are some things that you should always look at when you're doing exploratory factor analysis. We'll start with a KMO and Bartlett's test of sphericity. That'll give us just the basic test of whether or not the data are factorable. We'll also look at the anti-image correlation matrix. I'm not going to use the reproduced values here, although that's something that people often do. Then onto extraction. And you can see that SPSS has as a default setting principal component analysis. And, I followed the guidance from Fabregat and Wegner that principal component analysis really is not the best for exploratory factor analysis. There's some relatively complicated reasons why that's the case, and I won't go into that here. But I'll just say that I prefer principal axis factoring as an extraction method. You can see that we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8 different options here. And there are many others if you have a program like M+ or Urbano Lorenzo Seva's great factor program. Both of those have additional options that SPSS does not have. So we'll limit what we're talking about here, just the principal axis factoring. I'm going to take a look at the scree plot. And in a moment, I'll come back and I'll show you what to do if you want to use something other than the eigenvalue greater than 1 rule. So we're going to just continue to see what our basic extraction and rotation is. SPSS has no rotation set up as a default. And again, following the guidance of Fabregat and Wagner, I don't like very max rotation. I much prefer direct Obermann. And I've used some of these other ones as well. Just like with extraction, there are many different other types of rotation that are available that do not show up in SPSS, at least not in the vanilla version. I'm not sure, maybe there are some plugins that can do that. But if you use R programming or M+, then you can access those. So we'll hit continue with direct Obermann rotation. I always look at every single one of the options tabs here to see if there's anything I need. I don't need anything here in scores, and in options, you want to check the sorted by size function, because when you look at the rotated factor structure, if you don't have this checked, it's going to have the items in sequence from 1 to 13 in their original sequence. But I'd much prefer to have a rotated factor structure table that shows the factor loadings in sequence by size, by order of magnitude. So you need to check this box. All right, so we hit continue, and now we're ready to go. So just to recap, descriptives, we do these two, the KMO and anti-image. In extraction, we change it to principal axis factoring, check the scree plot. In rotation, we put it on direct Obermann. And then in options, we check the sorted by size. So we've got about 5 or 6 different toggles that we need to either change or activate. Hit continue, and we have our results. So when we take a look at these results, there are a few things to take note of. First, our KMO score, Kaiser-Meyer-Olkin, that's the overall test of factorability, and we want that to be high. According to some guidance that I've read, having a score at 0.8 or higher is excellent, and anything between 0.6 and 0.8 is, okay. Now, this isn't anything to get excited about. This doesn't tell you anything really special. It just tells you that you can proceed, that you have enough variance here to go ahead with the factor analysis. Bartlett's test of sphericity tests the assumption that the correlations in the matrix are 0. That is to say that nothing is correlating with anything else. And we want this to be significant. Just like the KMO test, having this one pass at this stage is not anything special, but we want to check and make sure that it's working. So we want this to be less than 0.05, and it is. But that just gives us the green light. Both of these give us the green light to go forward. You want the KMO for the scale to be above 0.6, ideally up closer to 0.8 or above, so that this one is okay. It's nothing special. And you want the Bartlett's test to be less than 0.05 for significance. We see that this one is. Again, it's nothing special, but we want to make sure that we have that in place. Then moving down, you can see that I'm going to pass by all this anti-image covariance. I don't need that for what I'm doing here. And I'm going to focus instead on the anti-image correlation matrix. If you go down the diagonals here, the ones with a superscriptal letter A, those are the ones, those are the values that tell you the KMO score for the individual items. So item 1 has its own KMO score, and that's along the diagonal. And it's the same principle. You want it to be above 0.6, ideally up around 0.8 or above, and you can see that all of these ones are. So that just tells you that the items appear to be functioning well. Again, it's nothing special, but if you have a bad item, an item that's just filled with noise, and by noise, I mean people are responding randomly because the wording of the question itself is ambiguous or confusing, then you might be able to see it here with a very low KMO score along the diagonal. And then if we look along the off diagonal elements, let's just look at this first item. Going down this column, this would be for item 1. Think of this like a correlation matrix. So you have columns and rows, and if you go down the column, that's for item 1, the first column here on the left-hand side. You want these values to be small. This is the negative of the partial correlation for that item. And I'm not sure really what value would be an indicator of having a problematic score here, but I would assume that 0.5 or above, not 0.05, but 0.5 or above would be an indicator of having a problematic high score here. You don't want these to be high. How many would it take in order to be able to say that this is a bad item? Again, there isn't really very much clear guidance in the literature on this that I'm aware of. There may be something, but people differ in how they approach this. And so I think the best guidance would be if you see a whole bunch of high scores, and the ones that I've underlined, that's a sample. Let's say half of these were above 0.5. That would be a probable indicator that it's a bad item because it's just not working well with the other items. Again, this is the negative of the it's the negative of the partial correlation. So we would expect that the positive of the partial correlation would be strong for the item as it's correlating with the scale. And if that's the case, then these numbers should be small. So if both of these sort of preliminary tests of item value or decency, or I guess adequacy, these seem to be working well. All these items seem to be working well. But what you would do is basically you would go through this table and just see if any of these values down the diagonal are really low. In that case, you want to take a look at maybe the Cronbach's alpha loading for that particular item, or how it works in the rotated factor matrix. You might be able to spot the quality of having a bad item here, but you'd want to verify it elsewhere with some of the other tools available. So this is just your first pass at it. Next, we have the communalities, and the communalities tell you the amount of each item. So if we just focus on item 1 right here, this is the amount of this item that is explained by the combination of factors that we have. So we don't know yet what those factors are, but in general, we're explaining about 40%. That's 0.395, rounded up to 40.40. So we're explaining about 40% of what's going on in item 1 based on the factors, the factor loadings themselves. Next, we have the eigenvalues. And what we're looking for here is an eigenvalue greater than 1. That's the traditional rule that has been used since really the 1950s, or possibly even earlier. And what you're looking for is just a value greater than 1. And what that tells you is that that particular factor is doing more than its fair share of grouping the items. So you have as many as 13 possible factors here because there are 13 items. The numbers here do not refer to the items, but the factors. So if all of your scores for all of the people on all of the items were really uncorrelated, which is hard to do, but if you can imagine that, then you would have about the same values on all of these eigenvalues, and they would all be close to 1. They would all be popping out as individual orthogonal or uncorrelated factors. And we don't want that to happen. Actually, we want a small number of factors indicated by having eigenvalues greater than 1. we can see that we've got 4. And the eigenvalue rule, eigenvalue greater than 1 rule, has been criticized for being, a little bit too simplistic, that sometimes you have something that's very close to 1 that's popping up as a factor, but then something else that's just under 1 that is not considered a factor. Like, what's the difference between 0.99 and 1.01? It's a very trivial difference, but the second one would be considered a factor and the first one would not. 0.99 would not be considered a factor, but 1.01 would be, according to the eigenvalue greater than 1 rule. So a lot of people, there's guidance that a lot of people offer that you also want to look at the proportion of variance that's shared that were explained by that particular factor. So this factor covers 23.5% of the variability of the scale. And this last one only has 5%. Well, a little bit less than 5, 4.778. So I like to use what I call the 5% rule. And basically what that says is we're going to consider it a factor if you have an eigenvalue greater than 1 and at least 5% of the variance is explained by that factor. So we want to have both of those things in position. So this second, or rather this fourth factor here, this one right here, it passes on the first test, having an eigenvalue greater than 1, but not on the second test. And these are not significance tests or anything like that. These are rather informal, in my opinion. But we want to see both of these line up in agreement. So I'm not convinced that we have 4 factors. It could be 3 factors, in which case we'll need to tell SPSS to run it with 3 factors instead of with 4. And I'll show you in a minute how to do that. Next, we look at the scree plot. And the idea with the scree plot is that we're going to judge where the factors are based on the emergence from the scree. Scree is like, you can think of this like rubble at the bottom of a mountain. So you need to judge where is the inflection point between the rubble and the mountain. And you can see that I've sort of visually, informally drawn these lines here. And it is a subjective process. But the idea is that we'll use this line to determine what's a factor and what's not. This is one factor. This is a second factor. This is a third factor. And on the y-axis over here, you can see eigenvalue. If you extend the line directly over to the y-axis from this dot on the scree plot, that eigenvalue is the same as what's up here in the table. So for this third one, that would match 1.391 right over here on the y-axis. And the one that we're not sure about is this one here. It's really rather close to that scree. So the scree plot is used visually to determine the existence of a factor. And the scree plot here seems to be suggesting a total of 4 factors, but that last one is really kind of on the cusp. So I'm going to put this line back in. And it's this one here that we're not sure about. That's factor 4. This one that did not explain 5% of the variance. But we're still not sure because we want to look at the rotated factor matrix to check it out. And we're going to scroll down past the unrotated factor matrix. That's the first one. The pattern matrix is the rotated version. And so what we're looking for here is the factor loadings. What I do is I just highlight every factor loading that is above 0.4. Some people use 0.3, some people use 0.5. I think 0.4 is a good basis on which to make a determination of a factor loading. And specifically, what we're looking for here is that an item loads onto one factor with a score that's clean above 0.4 positive or negative, doesn't matter. If you had a reverse coded item, you'd have a negative sign here. But the important thing, the important consideration is that it does not load on any of these other ones. That would be a dual loading. So for this first item, which is item number 5 in our list, you can see that it's loading on only one factor, factor number 1, and it's not loading on any of these other ones. So that's good. We don't want a dual loading. We don't want to have a minimum loading that's less than 0.4, and we don't want a factor that only has one item loading on it. That would be what's called by some people a bloated specific or a pseudo factor. So we don't want a pseudo factor. We want to have at least 2 items loading onto the factor in order for us to think that it's real and not a pseudo factor. So we go down our list and we can see that we've got 1, 2, 3, 4, 5, 6 items loading onto factor 1. Factor 1 is doing most of the work here, it looks like. All of those 6 items load above 0.4, and none of those first 6 items load on any of the other items. So that's good. That's good. That's a nice pattern. For the second factor, you can see I've got 1, I don't like red. Let me go to that, change it to yellow. We've got 1, 2, 3 items that load onto factor 2, and none of those 3 items load onto any of the others, so that's good. I've got 1, 2 items that load onto factor 3, but neither of those items load onto any of the other factors, so that's good. And then I've got factor 4 has 1 item that loads above 0.4, and that's bad. That's an indicator that it's a pseudo factor. And this item here loads onto 2 different factors. So that's a sign that that's a bad item. And so that's item number 6. We're going to maybe take a look at removal of that item. But first, what I want to do is I want to change the number of factors, because this 4th factor appears to be a pseudo factor because it only has 1 item loading on it, and because it did not account for more than 5% of the variance of the scale. It was also pretty close to that break line in the scree plot. That 4th factor, that's right here. So we have a couple of different indicators. That factor 4 is a pseudo factor. It accounted for less than 5% of the variance of the scale. It only had 1 item loading on it. It's close to the break line of the scree plot. So there really isn't very good convincing evidence that we have 4 factors for this exploratory factor analysis. So what we want to do is we want to change the number of factors to 3. And I'll show you how to do that. We go to dimension reduction factor. And under the extraction options panel, you can see down here that we've got this section on how to extract it. And by default, it's set up to use eigenvalue greater than 1 as the extraction rule. But what we're going to do is we're going to change this to the fixed number of factors, and then you have to type in the number that you want. And I'm just going to tell SPSS that I want 3 factors. And so once we do that, we can run it again. Everything else will remain the same, except for the factor loadings table. That factor matrix is going to look different now. It's going to have 3 columns instead of 4. While I have this up, it might be worth mentioning, if you have a small sample and you're doing a factor analysis, sometimes you don't get a solution, you get an error message. One of the things that you might be able to do to fix it is increase the number of iterations right here. It's set at default at 25. I don't know why it's so low, because today's computers can easily handle much more than that. So you can up that to 50 or 100 or whatever you need and see if that solves the problem. Anyway, we're going to hit continue and OK. It's going to run it again. All of these values stay the same. Nothing here will change. The communalities will stay. Well, I think actually the communalities change a little bit. The eigenvalues will stay the same. except that that fourth one is now no longer showing up over here. So all of these values are identical to what we had before, but this fourth one is no longer showing up down here in the extraction sum of squares section. Scree plot also will stay the same, but you can see that the big difference is in the pattern matrix for the rotated factor structure, all the numbers in here are going to change because that fourth factor has been eliminated. Whatever variability was associated between the items and the fourth factor is now being grouped together with the other factors, and it'll make the numbers bounce around a little bit, usually get a bit higher. And scrolling down, we can see at the bottom, number 6 was the one that was problematic before, item number 6. It's this one: sex offender registries provide little benefit, little to no benefit. So that one was not working well. It's still not working well. So that's a sign that that particular item is a bad item. It's not performing well with the rest of the scale. And so we're going to take a look at removal of that item next. But first, let's see about this last factor here. The third factor has 2 items that load onto it, and item 12 is now no longer loading on anything. So number 6 and number 12, those appear to be bad items, and we're going to consider taking them out. But that's how you change the number of factors that you want. Let's take a real quick look at the Cronbach alpha. And so that's under scale, reliability analysis. I'm going to take all these items. We're considering a removal of items 6 and 12. Put those over. Cronbach alpha, you want to take a look at these options here, especially the last one, scale if item deleted. I'll run that, and we have a barely acceptable Cronbach alpha. Like the KMO, 0.6 would be considered, maybe okay. 0.7 is good, 0.8 is really good, and above 0.9 is excellent. So this is a sign that the scale is not working that well. I mean, it's a decent scale, but it could be better. And so going through the items here, I don't know if you can hear that siren going past my house. We're going to take a look at item 6 and item 12 for possible removal. Cronbach alpha currently is 0.663, and it says that if we remove item 6, it'll go up to 0.695, and if we remove item 12, it'll actually go down a little bit. But I'm convinced that those are both bad items, so I'm going to take those out and see what happens. Normally you do this one at a time, but I'm going to speed things up a little bit. I'm going to take item 6 and item 12 out because they just didn't work well in the factor analysis. And so now you can see that I have a Cronbach alpha after removal of those 2 items at 0.691. So it's a little bit better. And this last column for Cronbach alpha of item deleted, I mean, it's possible that some of these items are going to improve things if we take them out, but we don't want to mess around too much with it. You get to a point of diminishing returns because Cronbach alpha is partially determined. The magnitude of it is dependent on the number of items. So every time you remove an item, you also lose a little bit of the value of Cronbach alpha by removal of an item. But if it's an item that's not correlating well with the rest of the scale, then it should conversely make the value go up. So you have these dueling pressures wherein removal of an item in Cronbach alpha analysis, the reduced number of items makes Cronbach alpha go down, but if it's a bad item, it should make it go up again. Anyway, so I think this is, it's probably a good idea that we took out items 6 and 12. We're going to run the factor analysis one last time. There we go, dimension reduction factor. And I'm going to take out item 6 and item 12 and run the factor analysis again. Ideally, excuse me, ideally you would be doing this one item at a time, running it at each phase. So I'm going to keep the same setup, same parameters. Kaiser-Meyer-Olkin and the sphericity test, they're both still fine. Let's fast forward down here. The eigenvalues got a little bit better. These numbers went up a little bit by removal of those two bad items. So that's a sign that we made the right choice. If we look at the scree plot, now you can see that it's a little bit more clean in terms of having 3 factors emerge from the scree plot. So that's again, that's a sign that we did the right thing by removal of those 2 items. And then going down to the pattern matrix, let's evaluate the whole thing all over again. That's good, that's good, that's good, that's good, that's good, that's good. So all of those items loading onto factor 1. And then the rest of the scale. Let's see. We've got 1, 2, 3 loading onto factor 2 and only onto factor 2. And we've got 2 items loading onto factor 3 and only onto factor 3. So that's good. That's in what we call a simple structure. We don't have any dual loadings, and all of the items are loading at least 0.4. All of the factors have at least 2 items. This is these different points are part of the definition of what we call a simple structure to the factor analysis, and this is really the ideal of what you want to see. Maybe with a few more items and maybe a couple more items falling into factors 2 and 3. But overall, as an example data set, this is working pretty well now. I'd like to see Cronbach's off a little bit higher, but if we had some more items in there, maybe it would go up. All right, well, thanks for watching. Hope that was useful. Take care.